So we need some evidence to make our conclusion. So we assume we have collected the data. Last time I gave you some potential data we could get from the sample. Okay, we're going to have a look at this data. Okay, so generally, if the sample evidence is inconsistent with the alternative hypothesis, so in other words, if we think that green is greater than orange, but in fact our sample tells us that orange is greater than green, then of course we have no way of supporting our research hypothesis, and therefore we are going to throw the research hypothesis away. We're going to say, we thought it was a good idea, it looked like a good idea at the time, but the data don't give us any reason to believe that it was a good idea. On the other hand, the sample evidence may be in fact consistent with the alternative hypothesis. It is in fact possible that our sample tells us, yes, in the sample, the jumping jack people had a higher mean heart rate than the knee bend people. Well, in that case, you may want to jump to the conclusion and say, oh, therefore our alternative hypothesis is in fact true. Well, not yet. Can't do that. And this is really the big problem with hypothesis testing and with statistical analysis in general. If the data do not support in any way or are contrary to the alternative hypothesis, to the research hypothesis, then we can say, we have no support. But if the sample actually supports the alternative, we still need to be careful. We need to ask a very important question, which I can phrase in two different ways. Is it possible that what we saw in the sample happened by chance? So in other words, is it possible that the difference that we actually saw in the sample did not come up because there is a difference in the population, but because we were quite unlucky with our sample? So is it possible that the result of the sample could be due to a sample that was non-representative of the population? We still have to look into that question. That is the key piece of evidence we need. In order to make a little bit more sense of this key piece of evidence, we're going to measure this chance. We're going to measure it, of course, as a probability. And we're going to go back to that strange sentence that I gave you last time. So let's look at it once again. So we're going to ask now, using the hypothesis jargon, is if the null hypothesis is true, so assuming that in fact there is no difference in the population, what is the probability of obtaining data as supportive of the alternative as ours were, or more? Remember, we're assuming that we have a null hypothesis, but our data seem to support the alternative. So if the null hypothesis is true, what's the population of obtaining data supportive of the alternative, but just by chance? So this probability is the key piece of evidence we need. Again, you may want to think and look at this sentence a little bit more, see if you can paraphrase it, ask any question you want about it. But the point is that this particular probability is what we call the p-value. And yes, this p-value requires a little bit of celebration. It is a very important piece of information. It is the key, in fact, to understanding the conclusions of a hypothesis test, of a statistical analysis. And so we want to spend a little bit more time with this p-value. We're going to do that through examples, through exercises, and through thinking through it. As I said, just be patient, don't get frustrated. It will require still some more work. So let's work some more on this p-value. Okay. Now, this is a key concept and it's initially confusing. And one of the reasons is also because it works somewhat backwards. Not only it's confusing because its description, the way I have to describe it to you, is rather confusing, right? Assuming the null hypothesis, blah, 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 what happens, etc., etc. You may want to review that whole definition. But it also works backwards. Let's see why. Well, first of all, remember, this p-value is a probability. So it's going to be somewhere on a scale of 0 to 100. And I'm going to use percentages just to make things a little bit easier. Now, if the p-value is large, so something like that, okay, so we're close, well, no, fairly large value. I don't want to say close to what, but just a large value. So that means that the sample data was likely, the probability of seeing what we actually saw, assuming the null hypothesis was true, was pretty big. So in other words, we haven't seen anything unusual. We haven't seen anything strange. So that means that the null hypothesis is in fact credible. It's possible that it's true in the population. On the other hand, If the p-value is small, something like that, that means that the sample data was unlikely under the null hypothesis. So now we start to think about, maybe the alternative hypothesis is in fact true. So in fact, what we saw was not due to chance, because the chance of them happening was low, but is in fact due to the fact that the alternative is true. Now, what if the p-value is very small? And by the way, the p-value is usually denoted by just p. Okay. Well, if the p-value is very small, like what we're seeing right now, well, that means that the sample data was very unlikely under the null hypothesis. So if we assume that the null hypothesis is true, then we have to conclude that we saw something really, really rare, something really strange. Or maybe the null hypothesis was not right, and so the alternative was correct, and so in this case the alternative is going to be supported. So let's see how this all confusing thing works out in our good old example of jumping jacks versus knee bends. Okay, so in this particular question, remember that the null hypothesis was that the mean heart rate after exercise in the jumping jack and knee bend groups were the same in the population. Okay, and let's say that the data tell us that this p-value is 0.0007. That's actually the number I gave you last time based on some data that I collected in the past. Well, this is a very low number, very, very low number. So the data that we collected were not likely due to chance. So if we simply assume that the two mean heart rates were the same in both groups, well, the probability of seeing what we saw was extremely low. So either we saw something really rare, either the two samples that we collected were really unlucky, or probably the null hypothesis is not true, which means that the data supports the alternative hypothesis. Okay, so that means that the mean heart rate in the jumping jack is greater. Jumping jacks are more strenuous. Okay, but remember, we have to be careful. We can't do that with certainty. It's still possible, although very unlikely, that what we collected was unusual. Okay, so this is something again that we need to work with very, very carefully.